Our company was founded in the third year of the Taisho era and has been operating for just over 100 years. Currently, our headquarters is located in Annaka, Gunma Prefecture, and we are providing the mining, production, and sales of bentonite products. We are also providing the production and sales of related finished products. As a bentonite specialist, we have pushed through the 4 eras of Taisho, Showa, Heisei, and Reiwa. As we made it through 100 years of dramatic change, we will continue to work with the resources of the earth. Since the Hojun Group was founded, we have continued to work to provide clay mining resources, in particular, starting with bentonite cultivated through earth activities as a basic material in every industry in order to achieve wealth and prosperity. Of the bentonite production areas in Japan, our company has mining operations in Annaka City and Tomioka City in Gunma Prefecture and Aga Town in Niigata Prefecture. In addition, in terms of worldwide bentonite production areas, Japan is the second tier behind the US, China, Turkey, and India. Bentonite is used in various applications. Of these, purified organic bentonite is being used and considered for use in the fine chemical industry. For the fine chemical industry, we are introducing the Ben-Gel series for water-based absorption applications and thickening applications. Of these, Ben-Gel W100 is recommended for high dispersiveness, low viscosity requirements. Ben-Gel W100U and W300U are recommended for high viscosity requirements. Ben-Gel SH is recommended for high thixotropy requirements. For organic solvents, selection is available depending on the type of solvent to be used. When using an aliphatic solvent, the use of organic bentonite with an aliphatic modifier is recommended. Representative products include S-Ben N400, S-Ben NX, etc. When using an aromatic solvent, the use of organic bentonite with an aromatic modifier is recommended. Representative products include S-Ben NZ, S-Ben NZ70, etc. When using a special solvent other than those previously mentioned, laboratory prototyping is available. Volcanic ash forms montmorillonite due to geothermal heat and pressure in the ocean over several million to several hundred million years. And bentonite is mined as mineral ore containing this montmorillonite. Bentonite is a natural clay mineral with montmorillonite as the primary component. When the montmorillonite contained in bentonite absorbs water, it exhibits the characteristics of swelling and becomes sticky. In addition, bentonite is formed from volcanic ash falling and piling up when a volcano erupted several tens of millions of years ago, and so does not deteriorate over time. Bentonite is a common name for clay containing montmorillonite, and montmorillonite belongs to the smectite group that has a swelling function. Ore mined contains roughly 30 to 40% water. The surface feels moist when touched, and not hard like a rock, but is soft enough that it can be scratched using a fingernail. Our company uses bentonite as a raw material in various products. I will introduce these products. Montmorillonite is extracted from the mined bentonite to produce purified bentonite. This generates the Bengel series. Other products are produced through additional various modifications. Organic modified bentonite for water systems includes Bengel W100, Bengel SH, Bengel W100U, W300U. We also offer the S-Ben Organite series for organic solvents. The structure of montmorillonite is a stratified structure, or a sheet structure. The crystal structure of this sheet structure has a thickness of 1 nanometer. It is several hundred nanometers in the lateral direction. The crystal structure is set up like this. The characteristics of montmorillonite are that the crystal layers hold a charge, and that it holds exchangeable cations in order to compensate for this electric charge. The amount of charge held by the crystal is called the crystal exchange capacity. The properties of montmorillonite change drastically depending on differences with the exchangeable cations. For example, if a monovalent cation, lithium or sodium, exists between the layers, water will hydrate around the cations and cause dramatic swelling. In contrast, if divalent cations, calcium or magnesium, exist between the layers, it will demonstrate limited swelling or a small amount of swelling. The swell volume appears smaller in comparison to cations that are monovalent. Montmorillonite swells upon contact with water. In a dehydrated powder state, it is approximately 4 milliliters or 2 grams as shown on the right. However, upon contact with water, it is apparent that the volume grows at or above 10 times as shown on the left. This swelled montmorillonite can be dispersed by shearing, such as by agitation. These scattered particles generate viscosity in the suspension. Furthermore, as the dispersed particles have a negative charge on the surface and a positive charge on the end face, when shearing is stopped, it forms an association structure called a card house structure. Thixotropy is generated in this manner. To illustrate, it becomes watery when shaken and jelly-like when left untouched. Summarizing the characteristics of montmorillonite, its size is 1 nanometer thick plate crystals and are around the same size as carbon nanotubes. The surface area of the plate crystals is around 800 square meters, which is around the same surface area as 3 tennis courts per 1 gram, or 1 teaspoon. Its greatest characteristics are that it demonstrates self-swelling and expresses a reversible viscosity. Furthermore, there are characteristics such as that it has ion exchangeability, has high heat resistance due to being an inorganic mineral, has a high level of safety such that it can be used as a food additive, and has little degradation over time. There are some differences depending on the product. However, the general characteristics of montmorillonite are shown in the following table. We We manufacture and sell purified bentonite by extracting montmorillonite as the main component from bentonite extracted from mines. Purified bentonite is classified by its resulting viscosity, color, and cation type. The main products are Bengal, Bengal HV, HVP, Bengal Flake, Bengal FW, Bengal Bright 11K, Bengal Bright 23K, Bengal Bright 25K. Product properties are adjusted to meet the varying fields of use requirements, such as thickeners for water-based paints, pigment anti-settling agent, anti-drip agent, thickener for cosmetics, fat and oil absorbents, clarifying agents for the food industry, additives for building materials, etc. Favorable dispersion is recommended for effective use of purified bentonite. This is an introduction for such a dispersion method. Methods of dispersion include physical dispersion processing and chemical dispersion processing. Physical dispersion processing methods include 1. Raised agitation speed over a long period of time. 2. Raised temperature. 3. Using a high shear disperser. 4. Ultrasonic dispersion. Dispersiveness can be improved by combining these methods. Next is the chemical dispersion processing method, which uses the electrical properties of montmorillonite and includes 1. Addition of anionic surfactants, and 2. Addition of alkaline substances with sodium or lithium. In 1, dispersiveness is improved by using the absorption into the crystallized end face. In 2, the advantages of improvement in the repellent force based on the charge of the crystallized end face from pH and improvement in swelling based on interlayer exchanging with lithium and sodium are used. The main applications of purified bentonite are employing absorbability in applications such as absorbents and clarifying agents for food products, and employing its viscosity properties in applications such as viscosity modifying agents for cosmetics and paints. Applied as an absorbent, for example, it can be used as a clarifying agent to absorb and remove impurities in wines due to the large surface area of bentonite. Applied as a viscosity modifier, for example, it can be used as a viscosity modifier for cosmetics, as an anti-drip agent for water-based paints, and as an anti-settling agent for pigments. Purified bentonite can also be used in mold coating agents, textile-related industries, abrasives, pharmaceutical industries, etc. The purified bentonite recommended for these applications is extracted from mines as bentonite and manufactured and sold by extracting the main component of montmorillonite. Purified bentonite is classified by its resulting viscosity, color, and cation type. The main products are Bengal, Bengal HV, HVP, Bengal Flake, Bengal FW, Bengal Bright 11K, Bengal Bright 23K, Bengal Bright 25K. Product properties are adjusted to meet the varying fields of use requirements, such as thickeners for water-based paints, pigment anti-settling agent, anti-drip agent, thickener for cosmetics, fat and oil absorbents, clarifying agents for the food industry, additives for building materials, etc. This is an introduction of an anionic polymer composite montmorillonite product, where montmorillonite is extracted from bentonite and anionic polymers are combined with layer surfaces. The electrical repellent force becomes stronger and dispersiveness is improved by modification of the anionic polymer. Therefore, it has characteristics of a high repellent force even in an aqueous electrolyte solution, as well as low viscosity. An anionic-based polymer and montmorillonite composite fluctuates less readily in various types of aqueous electrolyte solutions. The table shows the concentration where various types of aqueous electrolyte solution coagulates. Bengal W100, which is an anionic-based polymer and montmorillonite composite, is used for bathwater additives and cosmetics. This is an introduction of silane-treated montmorillonite products, where montmorillonite is extracted from bentonite, and a silane coupling agent is modified onto the layer end faces. While the surface is left active towards water, the end faces show hydrophobic tendencies based on being adorned with a silane coupling agent. Therefore, the end faces of the particles that were swollen and dispersed develop a hydrophobic bond in water, showing high viscosity and high thixotropy. Silane-treated montmorillonite is considered to form an association structure as a developed arrangement of end-to-end crystallized particles due to the hydrophobic bond between the alkyl chains of the alkyl trialkoxysilane added on the crystallized end faces, and as a result, viscosity and thixotropy are improved. This graph shows the apparent viscosity of montmorillonite and silane-treated montmorillonite in an aqueous dispersion at various concentrations. It can be seen that there is a great improvement in viscosity with silane-treated montmorillonite in comparison to untreated montmorillonite. Bengal SH, which is montmorillonite with this type of silane treatment, is used in water-based paints and in anti-settling agents for water-based cutting fluids. This is an introduction of a polymer and montmorillonite composite, where montmorillonite is extracted from bentonite and the montmorillonite and carboxyl vinyl polymer are combined. There is a major thickening effect due to compositing the carboxyl vinyl polymer and the montmorillonite, which shows a high viscosity of around several thousand millipascal seconds at around 2%. the Bengal W100U and W300U, which are montmorillonite with compositive carboxyvinyl polymer, is used as a thickener and emulsifying stabilizer in water-based paints and resins. Organic bentonite is manufactured by swelling and dispersing by purified bentonite and montmorillonite in water, and ion exchanging the exchangeable cations on the layer surface with quaternary ammonium. When the cations which required for montmorillonite to swell with water are modified to surfactants, it demonstrates hydrophobic tendencies, or tendencies of not mixing well with water. This is then evaporated, dehydrated, and pulverized in manufacturing. Regarding properties of organic bentonite, characteristics differ depending on the type of quaternary ammonium. Our company uses these 4 types of quaternary ammonium. As a general tendency, an organic bentonite modified by quaternary ammonium with a benzyl group is compatible with aromatics, and quaternary ammonium with several sterile groups is compatible with aliphatic solvents. In addition, quaternary ammonium with few alkyl chains tends to be compatible with solvents that have a relatively high polarity. In addition, compatibility can be achieved with a wide range of solvent types by changing the modification amount or modifying 2 types of quaternary ammonium. Our company performs this process at the Nihon Yugi Nendo Company Limited in Mie Prefecture. Organic bentonite manufactured in this manner is swelled and dispersed in an organic solvent, and thickening and thixotropy are generated based on the association structure. The characteristics of organic bentonite are that it swells and disperses in an organic solvent through ion exchange of the exchangeable cations with quaternary ammonium. There is an appropriate type and amount of quaternary ammonium according to the type of organic solvent. The particles that swelled and dispersed in the organic solvent provide thickening, and the dispersed particles generate thixotropy through reorientation. There is little effect based on temperature due to the use of inorganic minerals. Organic bentonite is manufactured by modifying the layer surface of montmorillonite extracted from bentonite with quaternary ammonium. For organic bentonite, the products are classified by the classification particle diameter, type of modifying quaternary ammonium, and modification amount of the modifying quaternary ammonium. Representative products include, for the S-Ben series, S-Ben, S-Ben-E, S-Ben-W, S-Ben N400, S-Ben-NX, S-Ben-NZ, etc., and for the Orgonite series, 2 micrometers or less, Orgonite, Orgonite T. Favorable dispersion is recommended in order to efficiently use organic bentonite. This is an introduction of the physical dispersion processing method and chemical dispersion processing method. A high shear processing method is one of the methods of physical dispersion processing. Higher viscosity is observed with higher shear processing in all solvents. An increase in viscosity indicates the dispersion is promoted. A heat dispersion processing method is one of the methods of physical dispersion processing. Higher viscosity is achieved by heating. An increase in viscosity indicates that dispersion is promoted. Next is an introduction of the methods of chemical dispersion processing. The addition of a polar activator is a chemical dispersion process. Polar activators that function as dispersants include 1. Alcohols, 2. Acids, etc. The addition of a suitable amount of a polar activator will act as a dispersant for organic bentonite. The recommended sequence of adding a polar activator is to add it at the same time as putting the organic bentonite in the solvent for dispersion, or to add it after putting the organic bentonite in the solvent. Please make the addition based on one of these sequences. If the polar activator is added to the solvent beforehand, the polar activator may be absorbed around the non-dispersed particles and become a cause of inhibiting dispersion. The function of the polar activator can be considered as follows. In nonpolar solvents, there is a condition where it is difficult for nonpolar solvents to penetrate in between organic bentonite layers by themselves, which generates difficulties for swelling. Regarding this condition, the polar groups of alcohols and acids in polar activators will attempt to develop hydrogen bonds with the oxygen atoms present on the crystallized end faces of montmorillonite, enabling interlayer penetration. This stimulates penetration in between the layers of nonpolar solvents, promoting dispersion. In this manner, materials that demonstrate hydrogen bonds will function as polar activators. When using alcohols as polar activators, alcohols with short hydrocarbon chains are effective, as the hydroxy group performs the function. There is a suitable additive amount regarding polar activators. A small amount would yield an insignificant effect as a dispersant, with low viscosity as a result. At a suitable amount, there is sufficient swelling, enabling effective dispersion through agitation, etc., leading to an increase in viscosity. If an excess amount is put in, the increase in solvent with a high polarity will begin to cause flocculation. There is an appropriate organic bentonite and an optimal amount of its polar activator for the solvent to be used. While there are various additive amounts of this polar activator according to the type of organic bentonite and type of solvent, an approximate optimal additive amount is around 1 mol per 100 grams of organic bentonite. With a favorable dispersion method and a suitable amount of a polar activator, organic bentonite will attain favorable dispersion and association and thicken in an organic solvent. In addition, here are additional examples of the effects that additional agents have on dispersion. As an anionic surfactant will adsorb onto the crystallized end faces and cap the portions that generate thixotropy, this causes gel disruption and decreases viscosity. This is sometimes used to promote dispersiveness and decrease viscosity. Non-ionic surfactants have a property where a part has a strong bond with water, causing water required for association to be taken away, decreasing viscosity. Similar to anionic surfactants, as association structures are not formed, it is sometimes used to promote dispersiveness and decrease viscosity. In order to use organic bentonite as a rheology control agent, it is necessary to perform separation and dispersion of the laminate layer of the organic bentonite in an organic solvent. In order to do so, it is effective to use an appropriate physical dispersion method and chemical dispersion method at the same time. Sufficient dispersion will generate thixotropy in the organic solvent. The paint drip test is an example of the effect of thixotropy. This shows something painted with paint using a comb-shaped implement, which is then stood vertically immediately afterward. As it flows down, the paint thickens in stages. The addition of organic bentonite grants thixotropy, controlling the dripping. Although these were examples, they show the general physical properties of S-Ben N400, which is an organic bentonite. Organic bentonite shows viscosity and thixotropy properties in an organic solvent, an anti-drip agent for paint ink, and pigment anti-settling agent, a lubrication agent for oil boring, a viscosity modifier for cosmetics, a viscosity modifier for cutting oils of brittle materials. These are some of the things it can be used for. In addition, organic bentonite is used in sealing agents, adhesives, resin additive agents, greases, etc.